student at Pontificia Universidad Católica de Chile. And this is a work mainly related to the study of this very beautiful star-forming region called NGC 6357. And this is made with the BBBX survey. So just to give you some context about this region, so here I'm showing you just a part of this region, which is very young. We know that it has an age of about 1 to 1.5 mega years, and it is located at a distance of about 1.7 kiloparsecs, so it is farther than Orion or Taurus, for instance. But the main issue when we study this region is that the extinction is very high. So that, so the visual extinction in the literature has been pointed as almost 6 magnitudes. And that's why the BBBX survey, it's a very suitable data set to study particularly its stellar content. So it is expected that 10,000 YSOs, or young stellar objects, are part of this region. And it also possesses some of the most massive stars of the Milky Way. So these stars have almost 100 solar masses. So what we did was to take advantage of the first 8 years baseline of the BBBX in order to obtain the proper motions of the stars and the light curves using PSF photometry. This is a work made by and explained also in Contreras Ramos from 2017. So this data is not completely public. Another important feature of NGC 6357 is that it is expected that a trigger star formation event happened in the region. So there are several indicators of this. For instance, there have been found virialized gas clumps that could lead to the formation of protostars. And also, as it possesses very massive stars, their intense UV field can also push the gas or the remaining gas, and this can lead to the compression also of parts of this gas. And also related to this are these pillars or elephant trunks that are found here in this part of the region that have been associated to ionization fronts coming from these massive stars. So it is a very interesting region for us, and if we even zoom out into this region, so I was showing you just this part here, but what we see now is that this region is composed of 3 stellar clusters that are located here with these yellow circles. But these stellar clusters are also interacting with H2 regions here in these cyan circles, and it also possesses bubbles. So these bubbles are regions with lower levels of dust, and the location is marked with these white ellipses. So the dimension of this region is more or less this. Oh, sorry, I forgot to mention that this is a Spitzer image, RGB image. So you can see here the bands and the colors and the filaments of the region. If we zoom out even further, and now we move to the red band of the SS, what appears is this optical or big shell that you can observe here with this extension of about 30 parsec. And the presence of this shell has been associated to a supernova event, but its origin is still debated in the literature. And now I'm showing you in this green rectangle the image that I showed you before. Now, what we did to study the star-forming region, particularly the members of this star-forming region, was to first look for the members associated to NGC 6357 from the literature. And I'm not going to enter into much detail about the 3 catalogs that we consider, but the first one was MISTIX, that uses several data from Chandra combined with infrared to select young stellar objects from several star-forming regions. And this catalog was complemented with the MIRES one, which basically consider near infrared and mid-infrared data in order to look for SEVs that resemble the ones of YSOs. And finally, we also consider this X-ray census made by Wang and collaborators in 2007. And combining these 3, what we found was 2,500 unique members from this star-forming region. What we did was to look for them in our VVVX database, and here I'm showing you first the kinematic analysis. So we have here the vector point diagram for, in gray, I hope you can see them, are all these stars that are in the same region of NGC 6357, and in black what we have are the stars that have available proper motions in our VVVX dataset. So these are 1,600 stars. Now, what we noticed was that these stars cluster around two mean proper motion values, with the limit of these two overdensities of proper motions, as we call them, being this vertical line here. So these contours are for all the stars in the NGC 6357 field, but if we just consider the stars here in black, the ones that are the members, we have here the vector point diagram just for them with the contours superimposed, and you can see how they cluster around these two values of proper motions, forming two overdensities. So in order to look for the origin of these two different kinematic populations, what we did was to, based on a Gaussian mixture model, fix two limits in order to select stars that belong to the different kinematic populations. So the limits are here, I'm showing you these limits, and we define them as the red population of stars with stars having these values in the proper motion in the galactic longitude coordinate, because in that coordinate is where they deviate the most. And also we consider this limit to define the blue population or the blue kinematic population of stars. And if we divide these two populations and plot their spatial distribution using this Atlas-Gal map in 870 microns, which basically traces the dust or dust emission. So what we found was that the stars from the red population were mostly located in dusty regions. And this is further highlighted here in this plot, where we have the logarithm of the pixel value from Atlas-Gal against the galactic longitude proper motion. So we can see a trend here where the red population of stars have a peak of this pixel value that is higher than for the stars from the blue population, of the blue kinematic population. So the red population, it is more associated to dusty regions. Now, if we consider the Spitzer image in 8 microns, what we did, this Spitzer image is highlighting the filaments of the region, and what we did was to superimpose on them the proper motion vectors of the two kinematic populations. So what we observed was that for the blue population of stars, they seem to move more randomly, so they could be more relaxed, they could have had more time to interact. But the thing is that when we look to the red population of stars, what we see is that the proper motion vectors seem to follow the filaments of the region. So this led us to think that this could be a putative young population, or at least it is younger than the blue population of stars. And this could also be associated to the trigger star formation event that is expected for this region. Okay, so that was the first part of this work, and the second part is related to the variability. As I mentioned, we also have light curves in our data set. So the idea was to compile a catalog of light curves in the K-short band, but we applied several filters in order to have like high quality light curves for young stars in this region, and we ended up with a number of 774 light curves associated to young stars in NGC 6357. The bulk of these stars is mainly related to T Tauri stars. This means low mass pre-main sequence stars, and we know that they are intrinsically variable, and they mainly have flux changes due to two physical mechanisms. So the first one is that they possess very strong magnetic fields, so they develop these dark spots in their surface that, coupled with rotation, will lead to more or less sinusoidal variations of their fluxes. And the other thing is accretion. So if these stars have accretion disks, we know that the accretion could be developed through the magnetic field lines. So they could develop these dust columns or dust substructures that when they pass through a line of sight, what we will observe is a dip or a decrease in the flux in the light curve. Now, also, when material arrives onto the surface of the star, what we will see is sudden increases of flux. So accretion can lead to these two different variations. Now, in order to see what is the physical mechanism that dominates the variability in each of the light curves, Cody and collaborators introduced two parameters that help us to do that. And these two parameters are the asymmetry and the periodicity parameter. So the periodicity of a light curve basically tells you if the light curve has a stable period, it is a quasi-periodic light curve, or if it doesn't, so it will be an aperiodic light curve. And then the asymmetry will tell you if the flux tends to increase for burster light curves, if it tends to decrease for deeper light curves, and if it has no tendency at all, so it will be a symmetric light curve. Combining these two parameters, what we can see is that we can obtain different classes, and you can see the different classes in these examples here. So we can have, for instance, quasi-periodic symmetric variations related to spots. Extinction will be related to dips, for instance, so the dips can be periodic or could be completely aperiodic, and the same happen with accretion. So we can have bursts that are aperiodic, or in a few cases, bursts that are going to be or are going to have a degree of periodicity. The thing is that these different classes can also be linked to the age of the stellar populations of the stars. So, for instance, we expect that bursters should be more frequent at younger stages or at younger star-forming regions, sorry. So what I'm showing you here is the vector point diagram again, but just for the stars that are part of our light curve catalog. And you can see that the two kinematic populations appear again. Here I'm showing you with the arrows the two populations. We look for the fraction of bursters first in order to see a difference between them. So you can see that for the population that we think it's younger, we found a higher fraction of bursters than for the population that we think is older. But if we move to the quasi-periodic symmetric variations, this means related to spots. Spots are going to dominate the variability of young stars in more evolved objects. So this means that accretion needs to be in a very low rate, or you don't have to have accretion. Unfortunately, what we found was that for the two populations, the fraction of objects classified as this is more or less the same. So we cannot say anything about a difference here. But if we move to the quasi-periodic dipping, so these dips that could be related to the presence of these dust columns, this type of variability has been related to stable accretion modes. And we expect that this type of accretion mode should be on lower accretion rates. And lower accretion rates means more evolved objects. So we expect that this should happen on older populations, and this is what we observe here. So we found that for the red points, you can see that they are more common in the population that we think it's older. But of course, this is limited by the completeness of our data. So it should be it should be taken carefully. Okay, so just to finish, thanks to the BBBX, we found two kinematic populations for NGC 6357. And we think that the one that we call the red population could be younger because it is related to dusty regions, and its projected movement in the plane of the sky seem to follow the filaments of the region. And this could also be related to a trigger star formation event. We also compiled a catalog of 774 casual light curves, and we classify them according to their degree of periodicity and asymmetry. And these two metrics also pointed to a difference in age between these two populations, but this is also limited to the completeness of the data. So that's it. Thank you.